Jai Hind students. So today we are going to talk about the another application of the PN junction diode, that is clamper. Previously we have discussed about the series clipper and parallel clipper circuits, series and parallel clipper circuits. Those circuits were used for removing a portion of the input signal. But what is clamper? Clamper is another application of the PN junction diode, and it is used to shift the DC level. So, for the signal reconstruction we use the clamper circuit. It is basically consisting of three components, that is capacitor, resistance and diode. There are the 5 important points which we have to keep in mind while we are dealing with we are doing the analysis of the clamper circuit. First is that it is consisting of 3 components, capacitor, diode and resistance. Second is it shifts the DC level. Third, the peak to peak voltage in case of clamper circuits remains same. That means if you are having twice of Vm at the input signal, then at the output you are going to get the output signal which will also having the same peak to peak voltage, that is twice of Vm only. Also, the fourth point is that we have the shape of the signal. The shape of the signal does not get changed, it remains same. Suppose you are applying rectangular input signal, then at the output again you are going to get the rectangular signal, and if you are applying sinusoidal signal, then at the output you will get only the sinusoidal signal. So, the shape of the signal will remain same. And the last and the foremost important point is that in case of clamper, we start the analysis when and only when our diode comes in the forward bias state for the first time. The reason being that the charging and discharging time of the capacitor is 5t. That means in order to charge the capacitor, it requires the 5 fundamental time period, and for the discharging also it requires this. So, if in the first half cycle your diode is in a reverse bias state, then we cannot start analysis because capacitor will not never get charged, because for the first half cycle it will be partially charged, and during the negative half cycle it will discharge and then charge and discharge. So, it will never be able to fully charged, and that's the reason we wait that first of all our diode comes in the forward bias state and our capacitor will get charged, fully charged, so that we can start the analysis. So, that is the very important point while you are dealing with the clamper, that you should wait till the time your capacitor does not charge or it will not get forward bias, diode will not get forward bias for the first time. So, let us start clamper. In this we are going to discuss the various types of the clamper circuits and we will study the analysis. So, here you can see that the clamper circuit is a circuit that will shift the DC level to another level. Actually, the positive and negative peak of the signal can be placed at the desired level with the help of the clamping circuits. So, as I said earlier also, that the clamper circuits are consisting of the 3 components, and the one component is the energy storage element, that is capacitor, another is a diode and a resistor. So, capacitor is responsible for shifting the DC level. So, whatever be the value of the capacitor, the DC level will get shifted by that amount. So, if you are going to get the negative VC, then the DC level will get shifted towards the downward side, and if the VC is positive value, then this DC level or the capacitor VC is a positive value, then DC level will get shifted upward. So, here you can see the circuit. This is the signal. Here we are having the DC level. This is the, so here we can see the positive, and clampers are categorized into 2 parts, that is positive clamper and the negative clamper. So, here this is the this is the input signal which is passed through the clamper circuit, and here is the DC level. This is the DC level, and here we can see that DC level gets shifted downward. So that means if DC level is shifted downwards means your signal is shifted upward. So this is the positive clamper. Whenever your signal gets shifted upward, then it is a positive clamper, and if your DC level shifted, your signal is shifted downward, then it is negative clamper. That means here we can see that the VC is shifted, DC level shifted upward because here VC is positive. Here the DC level has shifted downwards, so VC is negative. So whenever VC is a negative value, this is a positive clamper because the signal is shifted upward, and when VC is negative value, VC is positive value, that means the signal is shifted downward. So this is due to the negative clamper. So how do we start the analysis? So whenever we start our analysis, we always start with the analysis by examining that what will be the response of the input signal. That means whenever what will be the condition of the diode, means my diode will be, is it forward bias or is it reverse bias? Because we know that we can never start our analysis till the time our diode will not get forward bias for the first time. As I told you, why? If your diode is reverse bias in the first half cycle, then in that case your capacitor, suppose my circuit is something like this. Let us say my circuit is like this, and if I'll apply a signal, this is the signal. So for the first positive half cycle, I can see that my diode will be in reverse bias condition. So if it is in reverse bias condition, then this diode will be open, and if this diode will be open, then the current will be flowing in this direction. So I can see that the charging of the capacitor will take place through this loop, and here the RC time constant is very high. It will take around the 5t. That means it will require, to completely charge, it will require 5 fundamental time period. So 1, 2, 3, 4 and 5. So this is, it requires this much of time. So your capacitor will get charge, discharge, charge, discharge. So it will never get charged to the maximum value. So that is the reason we cannot start here analysis for the first half cycle. So we have to wait for the next half cycle so that our diode will get charged. So always remember, we start the analysis in case of clamper circuits whenever your diode will become in a forward bias state, will come in the forward bias state for the first time. So let us discuss this first circuit. Here we can see this is the, let's say this is the input signal we are applying. So during the time period 0 to T1, and let's say this is T2. So during the time period 0 to T1, so during time period 0 to T1, diode will be in a forward bias state because this terminal had positive potential and this will at negative potential. So this will make your diode forward bias. So it is the ideal diode. So diode will be forward bias state. Because diode is in a forward bias state for the first half cycle, so we can start our analysis. So here, when it is forward bias, so current will start flowing in this direction. So we always take the direction of the current clockwise, and rest things will fall automatically at the right place. So let us understand this. How does it work? So because my current direction is I have taken clockwise, So the voltage, the potential or the voltage across the capacitor will be Vc, and this plate will be at the higher potential and this plate will be at the lower potential. So if I'll write the KVL in the first loop for that. So 0 to T1, diode is forward bias. That means you can start the analysis, and now we write the KVL. So Vi minus Vc is equal to 0. So Vc is equal to how much? It is Vi. So because Vc is the positive value, so we will retain this sign. This sign is, we can retain this sign in the across the capacitor. Now, at the same time, when capacitor charge, our diode is forward biased. So there are the two things. One is the capacitor will charge to some value. We will calculate that value, and that is we have already calculated. And the second is the output voltage. So under this condition, what will be the output voltage? Let's say this is V01. So across this, it is offer you, diode is forward biased and it is an ideal diode. So I have considered it as ideal diode. So it will offer you zero resistance. If it will give you the zero resistance, that means the voltage drop across the diode will be zero. And we know that in parallel, that voltage is same. That means if across this resistance, across this diode voltage is 0, then automatically V0 will also be equal to 0. So V01 will be 0. Now coming to the negative half cycle, that is T1 to T2 time period. So during this time period, this terminal will be at the negative potential and this will be at positive potential. So this will make your diode reverse bias. So diode is reverse bias. So it will offer you infinite resistance. So if it is offering you infinite resistance, means it is open circuit. So now current will take this path. Here we can see that capacitor is already charged to the value Vi with this potential. Input signal is having this potential, and here you are having the output, that is plus and minus. This is V0 across the load. So if I write the KVL in the outer loop marked by the red pen, we can write minus of Vi minus Vc minus V0 is equal to 0. So Vc will be equal to, V0 will be equal to minus of, taking out negative sign, we are taking out negative sign outside the bracket. So it is Vi plus Vc, and the value of, let us say this value is Vm and this is also Vm. So I can say that minus of Vm plus Vm. So V0 is equal to minus of 2. This is, let's say, V0 2. So here we can draw the output waveform. So initially 0 to T1, output is 0. So I'll mark here 0. T1 to T2, your output is minus of 2 Vm. This is minus of 2 Vm. You see, initially this was Vm, this was Vm. Now with the here we can see that our DC load line has get shifted. It has shifted upward. It has shifted upward. If I shift my DC level upward, you see, then only I will get this output waveform. So here, because my DC level has been shifted upward by an amount of Vc, because Vc is positive and we know that DC level gets shifted by an amount of the capacitor voltage. So if the voltage is positive, DC level will get shift upward, and if the capacitor value is negative, then it will shift towards the, it will shift downwards. So here we can see that Actually the initial signal was, this was my initial volt signal. This was my initial signal. Now my signal has been shifted, DC level has been shifted upward by an amount of Vc, that is Vf. So this is how we can analyze our Klemper circuit. Okay. So let us take another example. This is the another example. This is the biased clamper. In the previous section, in the previous case, we have discussed about the unbiased clamper, because there was only 3 components connected, that is capacitor, diode and the resistance. And because in this particular example, we can see that one additional battery is connected, and that means if additional battery is connected, that means this is a biased Klemper circuit. So let us start our analysis in this particular case. So this is the input signal, and during the time period 0 to T1. So during the time period 0 to T1, this terminal is positive and this will be negative, and we are applying the plus 10 volts, and this plus 10 volt is greater than this 5 volts, and because this is a rectangular waveform, so therefore the moment you apply this 10 volt, this will be greater than this 5 volt, so diode will be in a reverse bias position. So 0 to T1, Vi Vi is greater than 5 volt. So diode will be reverse bias. So in the first half cycle, we can see that because our diode is in reverse bias state, that means we cannot start our analysis, because what is the requirement? That for doing the analysis of the Klemper circuit, we cannot start our analysis till the time our diode will not get forward bias for the first time, because initially all the capacitors are fully discharged, and until and unless our capacitor will not charge to some value, we cannot analyze our circuit. So that is the reason we can not start the analysis. So I can write no analysis. Now coming to the next half cycle. So now during T1 to, this is, I can write small t1. So during the time period T1 to T2. Now we are applying minus 20 volt during the next half cycle, the first half cycle. So it is Vi is equal to 20 volt, and this is minus and this is plus. So but because here you are applying the negative to the cathode of the diode, and also here you are applying the anode positive through this battery to the anode of the diode. So this will make your diode forward bias. So the diode is in a forward bias state. So if diode is forward bias state and this diode is considered as the ideal diode, diode will be short circuit. So when your diode is short circuit, that means we can start our analysis and the current will flow in the first loop. So when current is flowing in this direction, that means the Vc, this will be at positive potential and this will be at negative potential, because we know that current will always flow from the higher potential to lower potential. So now we can write the KVL for this. It is minus of Vi minus Vc minus 5 volt is equal to 0. So now calculate the value of Vc. shifting the VC towards the right hand side. So, I can say VC is equal to minus, and VI is 20 volts. So, minus of it is 25 volts. So, VC comes out to be minus 25 volts. So, what does it mean? That we have to change the sign across the capacitor plate, because the sign is showing that we have taken the direction of the current, opposite direction of the current we have selected. So, let us change the sign across the plate. So, I can replace this by minus and this is plus. So, this is plus. Now, coming to the, so first when diode get forward bias, we get two things. One is the capacitor value, capacitor will charge to some value, and second is the output voltage. So, for output voltage V01, we have to write the KVL in this loop. So, this is plus and minus V0, this is plus minus. So, if I will write KVL in this loop, it will be 5 volt minus V01 is equal to 0. So, V01 is equal to 5 volt. So, we get two values. One is the capacitor value, the value of the capacitor up to which it is charged, and second is the V01. Now, coming to the, because here we cannot start our analysis during the first half cycle. So, here we write the no analysis. During first negative half cycle we have done, and we have to do the analysis for at least one complete cycle. So, because here 0 to T1 there is no analysis, then it is necessary that we should do the analysis for the next positive half cycle, that is T2 to T3. So, for that reason I am starting our analysis for the next positive half cycle, that is T2 to T3. So, again T2 to T3, this terminal will be positive and this will be at negative potential with Vi is equal to 10 volts. This is 10 volts. So, and capacitor is charged to the value Vc is equal to 25 volts with this polarity. Mind it, we have to consider now polarity which is marked by green pen, because the Vc is coming out negative. Now, this positive and this positive, and together will make again our diode reverse biased. So, when diode is reverse biased, then the current will be flowing from the outer loop, this green one. So, again we write the KVL for the outer loop. So, this is plus Vi plus Vc and minus V02 is equal to 0. So, V02 is equal to how much? 10 plus 25, that is equal to 35. So, remember why I have taken Vc plus 25, because I have already account for the negative sign here by changing the polarity across the capacitor. So, this is very important to remember, that once you have changed the sign across the potential because of this negative sign, here you cannot take the value negative, otherwise that minus and this minus will become the plus. So, that you have to be very careful while you are dealing with the this type of equations. So, output comes out to V02 will be equal to 35 volts. So, here during T1 to T2, what is my output voltage? Plus 5 volt, and always remember we measure the value from the DC level. So, during 0 to T1, this is 0, T1 no analysis, T1 to T2 the value output voltage is plus 5 volt. So, this is plus 5 volt, and for T3 to T4, T3 to T4, I should redraw it in a better manner. I would like to draw this on the input signal itself, so it will give you the more clarity about this. So let us draw with the red pen. So during 0 to T1, no analysis. T1 to T2, plus 5 volt. So T1 to T2 it is plus 5 volt. This is plus 5 volt. And T2 to T3 it is plus 35 volt. So I'll measure again from this place. So this is 35. This is 5. So how much this will be? 30 volts. And you can see this is also 30 volts. Also, initially DC level was this. Now VC is equal to minus of 25 volt. So initially the DC level was this was 10 volt and this was 20 volts. Now you can see that our value, because this is what? This is 35 volts and this is 10 volt. This is this is 10 volts. So how much this will be? This is 25 volt. So initially my signal was here and it gets shifted downwards by an amount of the 25 volts. Suppose if I draw the output waveform here. This is my output signal. This is my output signal. Here you can see. So 5 volt. This is 35 volt. And initially the signal was this was 10 volt, this was 20 volts. See, this 20 and this 5, this makes 25 volt and which is equal to VC, and because your DC level is shifted from here to here, that means this VC is negative. So you can see that the peak to peak value remains 30 volts and DC volt value has been shifted by an amount of 25 volt, and because VC is negative, that means this VC is shifted to downwards. So this is how we can do the analysis of any clamper circuit. Okay. This is the another circuit. Let us take one more circuit where we can do the analysis. Here, instead of taking the ideal diode, we have taken the silicon diode. So again, start our analysis. So I'll mark this as the 0. No problem. I will redraw the input signal. This is VI, this is T. This value is taken as 12 volt, this is minus 12 volt. This is my input signal. So let us start our analysis. During the time period 0 to T1, 0 to T1, let me complete this one example. So, 0 to T1, diode will be in a forward bias state because here you are applying the positive 12 volts. So, this your diode will be in a forward bias state. So, when your diode is in a forward bias state, the equivalent circuit would be replace the silicon value by silicon diode by a barrier potential of 0.7 volt, and this is negative, positive, negative, positive. This is your 2 volts, and here I set the direction of the current. So, this is plus minus Vc. So, if I will write the, and this is your V naught. So, if I write the KVL in the first loop, so it will be, because my diode is forward bias, so that it will be Vi minus Vc minus of 0.7 plus 2 volts. So, this comes out, Vc will be equal to 12 plus 2 minus 0.7. So, this comes out 13.3 volts. So, this is my value of Vc. So, my capacitor is charged up to the value of 13.3 volts, and which is a positive value. Also, at the same time, you will get the some output voltage, that is V01, and that is minus of 2 plus 0.7. So, this comes out minus 1.3 volts. So, V01 is equal to minus 1.3 volts. Now, coming for the next half cycle. So, during T1 to T2 time period, T1 to T2 time period, my diode will be in a reverse bias condition, because this plus and minus, and this is minus and this is plus, this will make diode reverse bias. So, diode is in a reverse bias condition, and when your diode is in a reverse bias condition, then this will be the outer loop with this polarity. So, again we write the KVL, that is minus of Vi minus Vc minus V0 is equal to 0. So, V02 will be equal to how much? Taking out minus sign outside. So, Vi is equal to 12 volt and Vc is equal to 13.3 volts. So, this is equal to net is 25.3 volt with minus sign. So, this is my V02. So, let us draw the circuit. During T1 to T2, my value is minus of 1.3 volts. This is minus of 1.3 volts, and the value V02 will be equal to minus 25.3. So, it will be downward. This value is minus 25.3 volts. So, here you can see this was 12 volt, this was 12 volt. So, here this is 1.3. So, this is nothing but 13.3 volts. So, we can see that this was the initial DC level, and this DC level has been shifted upward by an amount of 13.3 volts, which is nothing but Vc. So, here you can see that the value of Vc is 13.3. So, again your peak to peak value will remain same, that is 24 volt, and DC level has been shifted upward by an amount of the capacitor voltage, and also the shape of the signal remains same. So, this is how we can analyze the various points. So, you need to remember 5 key points in your mind. First is, we start our analysis in case of clamper when and only when our diode comes in the forward bias state for the first time. Second is the peak to peak voltage will remain same. Third, it consists of 3 components, that is the energy storage element, and that is capacitor and a diode and a resistance, and battery is optional depending upon whether it is a biased clamper or it is unbiased clamper. peak to peak voltage will remain same, shape remains same, and DC level, it shifts the DC level, and DC level gets shifted by an amount of the value of the capacitor voltage. So, if capacitor voltage is positive, DC level will get shifted upward, and if VC is negative, then DC level will get shifted downward. So, this is how we can do the analysis of any circuit. So, this completes your clamper circuit, and if you have any query, you can always contact me in the college. Thank you so much.